you have anything that you need me to go over from the odds or the evens in section 1.8? Ready, set, go. Odds or evens? Anything you need me to go over? 35. Which one? 35. Anything else? 37. We don't like the 30s. Okay. Anything else? 35, 37. This is all in section 1.8. Let me go find the problem so we can look at them, because the odds you guys have already been able to. Hold on, pause. I need to change the default program for this. Okay. All better. All right, section 1.8. Anything else besides 35, 37? Patricia? 44. Oh my. There we go. 35 and 37 were in the same section. Yes. Do that later. Oh no. I'll do that later. Go away. How much do you guys like computers? Because right now, okay, there we go. Number 35 and 37, we're talking about compositions and domains. They specifically want us to go two different directions, F of G and G of F. Really quickly, on 35, 37, was calc chat weird? Well, you can check on calc chat. But, we'll talk about it really quickly. Remember, when you do homework, check the back of the book. If you got it wrong, and it's an odd, where are you supposed to go? To calc chat to check your work if you knew what you were doing. Right? Check the, try it first. Maybe I should actually say that out loud. Try it first. Check the back of the book. If you didn't get it right, and it's an odd, go to calc chat. Try to find your mistake. Come the next day with questions about, I still don't get it. Okay. 35, 37. Where's plugging in? So really quickly plugging in. I should be able to write because I'm in nice. There we go. F of G. G goes into F, right? So the F of G of X is the notation. So I would end up with the square root of X squared plus 4. Whenever you're thinking about domain, right, you have to think about the input. Now, question, what got put in first? Technically, the X into the G. So we have to look at G first and say, hey, how's his domain? But kiddos, how's the domain of G? All real numbers. Does G have any problems with domain? No. So then we say, okay, so X went into G, but there were no problems. So far, the domain is all real numbers. However, what has to happen next? You have to take all of G and put it into F. So don't worry about F's domain. He's not even going to keep this X for long. Look at G first. What's his domain? All real numbers. Then go ahead and plug G into F. And now say, what's this domain? All real numbers, because it's a square root problem. X squared plus 4 has to be greater than or equal to 0. But isn't X squared always a positive number? If you add 4 to a positive number, isn't that still going to be a positive number? So, is this square root really having any troubles right now? No. So are there any domain problems? No. So what's the domain for letter A of 35? All real numbers. Not because there wasn't the possibility of a restricted domain, but X into G, all real numbers, and once G went into F, that can never be a negative anyway. So domain, all real numbers, for sake of time, I'll just use the double line. But B, instead of putting G into F, what are you doing now? Putting F into G. So who are we going to look at first for our domain problems? F. I just changed problems randomly. I'm still on 35, I apologize. Now I'm going to look at F first. Ooh, does F have any issues? Yeah, this is square root. So X plus 4 has to be So looking at F really quickly, X plus 4 has to be greater than or equal to 0. Can anybody follow that and see that X has to be greater than or equal to negative 4? Just looking at F. x plus 4 has to be greater than or equal to 0. Because we always start with x goes into f. Ooh, but this guy has to be true for that to work. So I move the 4. X has to be greater than or equal to negative 4 because of f. And then what do I do with f? Where does he go? Into g. So then I go ahead and put the little square. Put the little square root. What happens when you square a square root? It gets rid of it. And so it looks as though g of f should have a domain of all real numbers. But the problem is, before f ever went in g, x had to go in f. And what restriction followed from that first step? This one. Which is why, even though the function doesn't show it, because of the process, I still have to keep the original restriction. So when you're doing compositions and doing domains, I think I even said this yesterday, I was like, oh, these are nice ones. It's not even going to be a problem. 35 was not a nice one. It was okay in the first one because G had no problems. He got plugged into F, and once I plugged that in, actually F didn't have any problems either. So that's why I had all real numbers. But for G of F, F had problems to start with. Plugging that in, it ended up that G was able to help out and take away those problems, but the problems were there to begin with. So I have to say X is or was originally restricted to B, and just because plugging in took that problem away does not mean that those original X's were still allowed or are still allowed to be included. They still have to be excluded. 37, probably something kind of similar. I'm not going to do A and B. Can you guys help me out? Which one is the tricky one? Only one of them is. G into F or F into G? Which one's going to have a restricted domain? Only one of them will. G into F will have a restricted domain. So let's look at that one as our other example. F into G, the domain is going to be all real numbers again. And I'm guessing the hardest part on this is the domain. So 37, A is the hard one this time. Because when I go to plug G into F, this one, I have to ask myself, first of all, does G have any domain problems? Does G have any domain problems? Yes. For G, what does X need to be greater than or equal to? Or X within bracket 0 to infinity parentheses. X has to be greater than or equal to 0 before G ever gets plugged in. What happens after G gets plugged in? Remember, use F's formula. Take G and put it in that input spot. What happens with the square root squared? X plus 1 is F of G, but what is my domain going to be? X is greater than or equal to 0 because X had to work in G before G ever got put into F. You have to kind of train your brain to know, look at the domain of the inside, and then plug in and check again. So looking at the domain of the first, X had to be greater than or equal to 0. Plug in, check again. Well, there's nothing extra. There's no problems with this. So the only problem was the original. Okay, that's 35, 37. Any quick questions or, I don't know, confusion that you guys have you can verbalize? All right. If you still don't like it, feel free. Come on in. We can talk it through a little bit. I can give you more examples. But we did have one other question. That was number, oh, it's a kitty cat. Number, and a dog. 44. They look a little closed. 44. Did I just give you 44 in this section? Okay, I was going to say, look now, these are great problems. Okay, 44. What are you supposed to use to solve for this? Did anybody read the directions that you were supposed to be writing down anyway? What do you think a lot of kids do when they get here? They're like, read the directions. You're supposed to write them down anyway. Sketch the graphs. You're supposed to be showing me the problem anyway. And then use the graphs, right? First of all, 44, what's the notation? What are you supposed to be doing for A? What does this mean? Subtract 1. F of 1 minus G of 1, right? Is this an X value or a Y value, the F of 1? What's the X value? value in this problem? Okay, x is 1, but what are they asking you to find? Plug in the x, and f of 1, f of x, that's not an x value, that's a y value. So when x is 1, what's the y for f? Minus when x is 1, what's the y for g? Oh, when you put it that way. When x is 1, what's the y for f? 2. Minus when x is 1, what's the y for g? Does that make sense, guys? Okay, to think about function notation. Inside the parenthesis is the x, or is the input. Put in a 1, get out. That's what the function does. The function outputs, or the function gives the y value. Colby, go ahead.
So we didn't have to find the actual function?
You guys made an absolute value function?
Yeah.
Why? Did you write the directions? Use the graphs. So what are you going to do for letter B? What's the notation say? Find the function f and g and multiply the 2 and then plug in the 4? No. What does it say to do? F of 4 times g of 4. So you guys tell me, how do I find f of 4? Go to the graph. Do what? Go to x is 4. Now what? Which is? Do the same thing with g. Dun, 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 dun. You guys making things too hard. Good job finding the functions if you were able to, but as you get higher, they give you graphs of things that you won't know functions for. All right, cool kids. Those were the 2 questions that I had. The rest of you guys, I told you to come ready with questions, and I gave ample time for you to ask. So, section 1.9, here we go. See, I had you write the directions for a reason. Sometimes you want to ignore them. Here we go, 1.9. Top books, 1.9. No. My dad likes the Broncos. George would always update me last year, so I don't know what's going on. I didn't grow up with cable, so I didn't really, well, not even. I had like a little, it never worked. So I didn't really ever have channels to watch football, and my dad never really forced us to. He likes it, but we never really had the channel. So, did you never grow up watching it? You know, do fantasy football or something? I can do that. I do watch the Super Bowl. Alright, here we go. And now for the commercial. Here we go. Inverse notation, or inverse function. Inverse functions in general. Why do I have the note there? You guys are smart enough. Why do I have the note there? Why do I say not the reciprocal? What am I trying to warn against? Why would you think it's looking at it? Good. -1, negative exponents usually mean flip, right? And -1 specifically usually means take what you have and it's 1 over it, right? So the struggle is, this is function notation. So if you need to write this for yourself off to the side, please do so. This is function notation. And actually it happens in more than one place, meaning it does happen here with f inverse of x, but it's also going to happen eventually in trig. I'm going to show you a quick little example just because. What do you think this refers to? It's actually in your calculator. What does this refer to? Nope. It's the inverse of sine. Now but that's where it gets struggled, because you're like, oh, sine to the -1, that's 1 over sine, that's, if you remember, cosecant. Probably most of you didn't. But that's not cosecant. Because the -1 is being written next to the function. It's sine of x, like f of x. And if the -1 is being put next to the function, like the -1 is being put next to the sine, this means sine inverse, the same way this means f And the same way, this might be a struggle. This might be a struggle to you guys as well. Because a lot of you want to think this is 1 over sine, but the problem is in your calculator, how do you do 1 over sine if you need to do 1 over sine? 1 divided by sine. You don't use the second sine button. If you have accidentally used that second sine button to mean cosecant, and you made it wrong. Anyway, long story short, this inverse notation doesn't just show up here, it does show up with trig as well. But right now, we're not focused on trig, we're focused on just f of x function notation. So, inverse. What is an inverse? If it's not a reciprocal, what is it? Do you guys remember anything about inverse functions? How to find inverse functions? Switch the x and y and solve for
Y.
Depends how you do it. It's either take a function, solve for y, or no. Erase that. Strike it from the record. Either take a function, solve for x, or switch x and y, solve for y. Switch for the guy who's entrenched, whichever way you go. Definition of an inverse. That's how to solve for it. If you guys notice, hey look, what you just said I have. But before that, what does an inverse actually do? The composition of a function with its inverse is always just x, the same way the composition of an inverse with its function is x as well. For every x within a domain, that is. And that might not seem super earth-shattering to you. But let me give you a second. You actually don't need to skip any lines on this page. And let me get an example ready for you. HPrecalc kids are learning about transformations. Just kidding. You guys did it. There's a couple sections on it. I gave you a function up on the board. Now I'm just going to write them off to the side. Try to see how much you guys can do mental math. You guys know the undo button, right? Don't you use it a lot when you're like formatting things or writing essays or making a project? The undo button. No, not calculator. Sorry, not here. The undo button. Inverse, I want you to think undo. But you're not undoing math that's already been done. You're undoing operations in a function. What are the different operations that you guys see in f of x right now? What's happening to the x? Okay, there's a cubed root. What else? The addition by 1 and the multiplication by 2. 3 things are going on. If the inverse function needs to, when this function is composed, or when there's a composition of this function with the inverse needs to undo all of those operations in f to just get x alone. It needs to strip away all the extra stuff going on. So, question. Let's see if we can mental math without switching x and y and solving for y. Let's see if we can go straight there. For the inverse, which I'm going to call g, but if we do it right, I'll also call it f inverse. I need something when plugged in that will undo the times 2, undo the plus 1, and undo the cubed root. So question, what's something that would undo? Well, the x gets plugged in here, right? G. I need G to go in, and first things first, I need to have it undo the 2. So what's going to be there? Over 2, or you could say 1/2, right? Do I need a 1/2? Okay. What else am I going to need? A negative or a minus 1. What else am I going to need? A cube. Now, can you guys figure out, is it going to be a cube around the whole thing, or a cube around the x?
Okay.
Okay, let's check it. So that's an x and this is a cube. Alright, let's check it. How do we check it? Plug it in. If we plug this into the x spot, you guys see how this might be a problem? Cube root of 2 times plus 1. 1/2 x minus 1 cubed. Can I cancel out the cube root and the cube right now? I'm going to have to actually cube this guy. Maybe the cube's in the wrong spot. Is there another place we can try to cube? Yeah, let's try making the x cube. Okay, now let's try it. What happens if we plug in? This is how we can check any 2 functions to see if they're composition. Cubed root of 2 times who? This guy. How does that work? Almost. Because what happens when I bring in the 2? That cancels out. So this one does cancel out. So I just have an x cubed. What happens? Oh, trouble. What happens there? Minus 2 plus 1 cubed rooted. Is that quite what I wanted if I just want to get x alone? No. Can I figure out how to fix this then? Yeah, let's make that a 1/2. I didn't want the 2, I wanted a 1. So make this a 1/2. What happens when I distribute now? Minus 1. Plus 1. Now what can I do? The 2 and 1/2 cancel, the negative 1 and the plus 1 cancel, and now what happens? The cube root and the x cubed, if I can actually write it correctly, is also going to reduce. Remember, the whole cube root cancels out. And what do I have left? Did I properly find f inverse? Yes. It's not just some random g, it's actually the inverse of the original function. Now, was that a very experimental way of approaching that problem? Yes. But what was I trying to show you? What does an inverse do to an original? It undoes every single operation that's in play. It undoes any roots. It undoes any powers. It undoes any additions, subtractions, multiplications. So what does this definition truly mean? G, when plugged into F, completely undoes all the operations, only X remains. F plugged into G, even if you do the original into the inverse, the same thing will occur, only X will remain. A function as inverse, they completely undo each other. Now, the nice thing is we don't have to stick with that experimental method. We don't have to stick with that guess and check sort of way of finding the inverse. Instead, we can go ahead and follow what you guys learned in Algebra 2, switch the x and y, then solve for y. But here's my word of warning. If you're trying to find the inverse, you're solving for f inverse of x. So when you solve for y, there's one extra piece to the puzzle. Replace y with f inverse of x. Let me go ahead and write that again because the negative 1 kind of looks like a 7. You need to make sure you have your notation down. So even though, yes, you do switch x and y, not thinking about the notation, just make a y, switch the x and y, solve for y. Remember, at the end of the day, you cannot say y equals. That was the original function. You need to rename that y and call it the inverse. Because, kiddos, were these two functions the exact same? No. So if I say y equals the original, I can't say y equals the inverse. That doesn't work unless I start using y1, y2, and that's just lame. So instead, we're going to have f of x be the original, f inverse be the inverse. But you have to make sure and be careful that you replace that yourself. The other quick note, do you guys remember what happens with domains and ranges of inverses? The domain of f is the same thing as? Yeah, they switch. The domain of f is the same thing as the range of the inverse, and the range of f is the same thing as the domain of the inverse. That's a negative one. The domains and ranges, they switch. The domains and ranges, they switch. Okay. You guys will need that example. We just did an example on the other page. That was way better than that one. That one's boring. Okay, graphically. Inverse functions are reflections across. Look at the graph. I've given you an example of an f of x over here on the left and its corresponding inverse over here on the right. F is gray, f inverse is black. If we just switch the x's and y's, switch the x and y, solve for y. If we're switching the x's and y's, I need you guys to see a couple of things. Go ahead and get my highlighter out and do that. Some of you were able to remember from last year that to solve for the inverse, you do switch the x and y. If you switch the x and y, the points switch. You take an AB on one graph, it ends up being the BA of the inverse. So all the points switch. And that's why all the domains and ranges switched. And graphically, what ends up happening is that you have a reflection, but not across the x, not across the y. What line is in between these two, guys? The identity function, y equals x. You can't see the functions because they're too light. This is my f of x function. This is my f inverse of x function, and this is my y equals x line. Because your x's and y's flip, because your domains and ranges flip, you have a reflection across the y equals x line, and maybe in some of your minds that kind of makes sense. Reflection, you're flipping, so when you're flipping points, you're flipping the y's and x values. So if they give you like a graph of one, they ask you to show the inverse, you don't have to find the equation like you guys did in last night's homework, some of you, or 2 nights ago. If they give you the graph of one side, just realize, oh, I can just reflect it, and go ahead and use that idea of if I was to fold, what would it look like on the other side? You don't have to go find the equations and being precise with your calculator. That's not the point. You guys have a swoop on one side, swoop on another? Now, don't write it down, just read, because I already have the answer there for you. What does it say to do? First of all, what does it say the relationship is between these two functions? Inverse. Can you guys see why? Did they somehow have to divide by 2 or multiply by a half? Yes. Did they somehow add by a 3 in order to cancel that one out? Yes. Oh, parentheses. Maybe that's what we should have done in our example. We ended up figuring it out after a while. In the graphing calculator, does it look like one of these is the reflection of the others around the y equals x line? Yeah. So if they were to ask you to demonstrate that, yeah, I mean, I suppose you graph it in a graphing calculator. You can graph it without your graphing calculator, right? They're just lines. The long story short is you should be able to either look or even just put in like the y3, put in y equals x, and you should see what's on one side is also on the other for whatever portions you're looking at. Anyway, graphing calculator, you might want to use zoom square to make it kind of nice and fitted. Otherwise, if it's skewed, it might look a little funny. But you should be able to see that on a graph as well. And technically, from the graph you guys just wrote a second ago, You just said an AB is on one graph, a BA is on another. So I already actually filled in this blank for you. Anybody figure out what's supposed to go there? Since domains and ranges switch, order pairs, switch is fine. Yeah. Everything's switching. Which is why these exact two functions that I showed you on the graphing calculator a second ago, and they were reflections across the y equals x line. What do you notice about just a few? I just pulled out a few of the points. What do you notice about their points, guys? Yeah. So if you have -1, -5 on one, you can have -5, -1 on the other. If you have this one having a y-intercept at 0, -3, this one's going to have an x-intercept at -3, 0. It's easy for our brains to be like, flip it, flip it, flip it, flip it, flip it. No big deal. Like, switch them. Switch the x's and y's. It's harder when we get to a graph to actually be able to work with it, but it's not too bad of a concept. So I want you to remember two main words with inverses. First one is undo. That's what it actually does. And the second one is switch. That's how the x's and y's behave. Undo is how they interact an original with its inverse. Switch is how the x's and y's, the domains, the ranges, and even the graphs, in a sense, behave. Okay, as we are getting close on time. Let me see how far I am from the end. I'm close, but not quite. It's because we didn't get to start it yesterday. So all we're missing, oh, that's random. Box is moving. We're missing the topic of one-to-one or invertible. So maybe you're writing notes for another 15 seconds. But let me quickly check out homework and see where technically you're allowed to stop. Tomorrow we're going to finish 1-9 and start 1-10. So tomorrow's going to be a mixed day. Finish 1-9 and start 1-10. It looks like we should be able to do homework almost all the way. Oh, we still have 7 minutes, don't we? I don't know why I thought we got out at 9:30. I'm still in chapel dinner. Okay, I have homework open, so if I need to limit it, I will. But we get to go a little bit longer. I know you guys are following my lead. Sorry. I was leading you, just not in the right direction. Where are we at? Special functions. These inverses are also functions. One-to-one is an adjective. A synonym for one-to-one is invertible. And if you're being really lazy, like sometimes math people are, you could just literally do the number 1 hyphen and the number 1. Same thing. These are all synonyms. They all mean the same thing. You might be responsible for different ones at different times. It's an adjective. It just describes a function. It's a special kind of function whose inverse, when you flip it, will also be a function. Usually on this, there are other words, and we are going to start there in just a second in our notes. But can I just kind of help you introduce this for a second? What function would you guys guess I'm drawing here? If you were to guess, what would you say I just drew? Parabola, and I'm probably just doing the parent function, so y equals 10. Okay. Question. Can you find the inverse of x squared? Okay. Algebraically, how would you do it? We just wrote it down a second ago. How would you find that inverse? Okay. So over here, we'll talk about, hey, we're trying to find the inverse. Switch the x and y. Solve for y. Solve for whoever's on the inside. And how do I solve for y? Okay. So I have the inverse as y equals square root of x. What did I tell you you need to do before you finish and box your answer? Good. What you have just found is the inverse. The question, does anybody have any issues with what we just did? Mathematically speaking. What do we ignore? What do we not think about? Technically, when you're supposed to get y by itself, couldn't it have been a positive square root or a negative square root? we would call an inverse function of x. But kiddos, is this original function truly invertible? Is it truly one-to-one? Why not? I want you guys to think about the graph with me. What would you do if I asked you to graph the inverse? Wouldn't you have to draw the y equals x line? If everything switches, if this parabola is going around what axis right now? What is it symmetric about? What does it have to switch to be symmetric about? So it's an inverse one. What's the struggle with his true inverse? If you're thinking about the algebra, that's good. This only describes half. You guys remember the parent function of square root of x? What does he look like? Half of the sideways parabola. So this guy is square root of x. This guy is negative square root of x. The question is, are both of them together one function? What do they fail? The vertical line test. So, is y equals x squared invertible or one-to-one? No, because when I invert him, what happens? The inverse is no longer a function. It is a parabola. It's a parabola shifted this way, but this is not a function. It fails the function test. In order to find the inverse of this function, a true inverse, I would have to have how many different functions? So y equals x squared is not invertible. It's not one-to-one. But here's the question. You guys can look at the square root of x, negative square root of x, and say, oh yeah, when I flip it, it fails the vertical line test. My question is, what characteristic in the original could I say the original fails that will always cause the inverse to fail as well? If the inverse fails the vertical line test, what does the original have to pass? Vertical is for the inverse. You gotta flip it for the original. So I'm gonna go ahead and write down the inverse is need to pass the vertical line test. So what is the original gonna pass? What we now call the horizontal line test. In order to be a one-to-one or invertible function, the original has to pass the vertical line test. But if it's going to be invertible, it also has to pass the horizontal line test. Not to be a function, but so that its inverse is also a function. So the weird thing is, this special characteristic says it's not enough to pass the vertical line test. You also have to pass the horizontal line test for this adjective to be true, for when you flip your inverse, for it to also remain a function. So, question, what if I was to give you something like this? Is he invertible? I've drawn him truly, I haven't messed up. Is he invertible? He's good, almost everywhere, but where does he fail? Is he a function? Yes. But is he invertible? No. Because he fails what new test? Horizontal. Kiddos, you should have enough to fully attempt homework. You might get a little bit stuck on the invertible one-to-one stuff. Do the best you can. I'll see you tomorrow. Bye. Homework number 9.
For once, it's
I know. See, it randomly gets warm in here. But when it's cold, it's nice. You guys can almost do all of homework. We'll see.